Okay, so we're picking this up from ionic crystals, and I said that metallic crystals are very similar. The difference is these electrons, which are represented here with the little black spheres, these electrons, instead of one area of overlap, if we were to draw the overlap, metallic crystal overlap looks like this, where the nucleus is there in the middle. But then the next layer of metal atoms overlap the previous layer. So what happens is these electrons are free to move from area to area. So let's say, for instance, you're trying to conduct electricity. You take an electron and you push it into the crystal, and what it does is it repels each of these electrons, and they're able to jump around and move through the crystal freely. We call that delocalization, and then the electron moves out the other side of the crystal. So copper wiring, really good for conducting electricity. There's very little resistance. Kind of think of the electron in a metallic crystal as an electron superhighway. It's not stuck in one level, one layer. It can move freely from one area to the next very quickly. And again, here's another three-dimensional way of showing electron delocalization, that the electrons, you can think of them as moving in between the metal atoms and free to do so. Again, we call that delocalization. This, believe it or not, is from the AP textbook. This is a silver crystal, and again, they're trying to show you that the electrons move freely in between those silver atoms. What's the mechanism? We're going to overlap these things just like covalent molecules. However, the overlap creates delocalization. That's the difference in terms of the properties. All right, so how does delocalization explain properties of metals? Well, for instance, to conduct heat and electricity, to conduct heat, you need particle collisions. Remember, we said the hot object, those particles are moving faster. The cold object, they're moving slower. When they meet at the interface, those collisions transfer energy. And in order to transfer that energy quickly, you have to have a lot of collisions. And that's much easier to do in a metallic crystal because the electrons are moving around freely. The last type of bond that they want to talk about in this chapter 12 is polyatomic ions. And polyatomic ions are what we call dative or coordination bonds. I like to use the term heterolytic. And heterolytic means instead of each atom contributing one electron, one of the atoms contributes 2 electrons and the other atom doesn't contribute anything. It contributes space for those electrons to move towards. Another term for this would be a dative bond, and sometimes the term coordination bond is used. And the reason why coordination bond is used because these dative bonds tend to form when you have d orbital space available for the electrons to move to, but you don't need to know that. All right, so example of polyatomic ion, ammonium. Ammonium is NH4+. And if we were to draw this using Lewis structures, I know you haven't done a lot with Lewis structures yet, you saw that one video. We would draw the nitrogen in the middle and the 3 hydrogens. And the nitrogen has an unshared electron pair. So the nitrogen has 5 valence electrons, and the hydrogens each have 1 valence electrons. And that would give us a total of 8 because there's 3 hydrogens. And we would say, okay, well, this satisfies the octet rule. Well, it does. And this creates a compound called ammonia, NH3. It's a very stable compound. However, in a water environment, you have a lot of H plus and OH minus ions floating around. And those H plus ions will become attracted to this unshared pair. And when that happens, what you get is this polyatomic ion, and they draw it with brackets for Lewis structures, and they put the nitrogen in the middle and the 4 hydrogens, and what they do is they put the charge outside the brackets. And the reason why they do that is they want to show that that charge is actually spread out throughout the whole entire ion. And the process of spreading out the charge is something called hyperconjugation. So I'm just going to say dispersal of, it's supposed to be an S, of charge. Dispersal of charge. So in this bond, nitrogen's providing both electrons, where this hydrogen isn't providing any of the electrons. All right, so what do they want you to know? I'm glad you asked. They want you to know the properties of this. So I'm going to come back to that slide in a moment. Let me dig up some nonsense for you that you can pause and put into your notes. Let's see, nature of, that's my hot and cold, and endothermic, exothermic, dynamic equilibria, real versus ideal gases, deviations to gas law, thermodynamic spontaneity. Here we go. Polyatomic ions. I would add this to your notes. Pause this and write them down. Nonmetals bond together covalently. That's the mechanism. However, this covalent bonding creates a surplus or deficiency of charge. And the way we deal with that charge is through what's called hyperconjugation. Instead of having all of the surplus or deficiency in one area, we're going to spread it out equally throughout the whole entire polyatomic ion. And this spreading out of the charge problem creates stabilization. And once it's stable, that ion can go on to create an ionic salt by combining with another ion. So you basically have covalent bonding inside the polyatomic ion, and then that leads to ionic bonding outside of the polyatomic ion. So it kind of has both things going on. Okay, and again, this shows my example with ammonia, with the unshared pair of electrons being attracted to the H plus ion and creating the coordinate covalent bond. Again, another example of coordinate covalent bond is nitric acid, HNO3, which has the nitrate group in it. And in the nitrate group, we have homolytic bonding, where each atom contributes one electron, but we also have some heterolytic bonding, and that heterolytic bonding is the coordination bond. And then that problem of the surplus of charge, when we say NO3, we say nitrate has -1 charge, but the oxygen doesn't carry the -1 charge. The -1 gets spread out throughout the whole entire ion. So good way of thinking of hyperconjugation. I always call it the Dr. Checker hair analogy. See if I can bring that up. Go to my camera and no, I can't go to my camera. Yeah, I can't do that because then it's going to mess up my video. All right, so I'm just, instead of Dr. Checker, it'd be any sort of bald guy. So I'm just going to draw a bald guy here. Here's a bald guy. And he's unhappy about not having hair. Right, I better draw the rest of his body here. Got his arms out here. He's unhappy. Hey, even me, I'm missing a lot of my hair. My hairline's receding now. So what you could do is, if everybody donated a little bit of their hair, just a little bit here, a little bit there, a little bit here, you wouldn't be missing it, right? It's just a little bit of your hair, but I could use that hair to cover up my baldness problem. And that's what hyperconjugation does. You have a problem, like being bald. All the other atoms contribute a little bit of charge density, a little bit of their electron cloud to the area that has the deficiency. They're not going to miss it. They have a surplus anyway. And the electropositive center is what takes on that deficiency. And so instead of leaving the deficiency the way it is, each of the atoms around it donate a little bit of their charge cloud to help cover up that deficiency. Now, it doesn't solve the deficiency. You still have this charge out here, right? This positive charge. What solves the deficiency is that positive charge will combine with, let's say, chloride and form ammonium chloride, and then that completes the problem. But it is a temporary solution, and the molecule, in this case polyatomic ion, is lowering its energy in an effort to stabilize by, again, we're going to donate a little bit of the charge cloud from the things that are electronegative, and we're going to spread them out and try to cover up the electropositive. So the bald person hair analogy on that one. Hyperconjugation is the term. You don't have to know it. It's advanced, but you're advanced people. Alright, so where was I? Last part of chapter 12 deals with these 4 radii: atomic, ionic, covalent, and van der Waal. And what they mean by radii is they're talking about the distance between a positive nucleus and a negative electron. For the atomic radii, we're talking about the distance from the nucleus to the outermost electron in an individual atom. Argon's a noble gas, even though they drew another argon next to it to show that it was an argon solid. This distance between positive and negative, that argon atom is acting on its own, so we call that atomic radius. Now, ionic radius for sodium ion is, again, the distance from the positive nucleus. Let's write ionic radius here. To the outermost electron in an ion. And that radius depends upon which ion we're talking about, because for chlorine it would be larger radius as we start for the chlorine nucleus and we go out to its outermost electron edge. Again, they're looking at 181 picometers compared to 102 picometers. Picometer, by the way, is a trillionth of a meter. And chlorine molecule, Cl2, we overlap the 2 chlorines. So if I draw this as overlap, right, then we would say, all right, the distance between the 2 nuclei, and what you're going to do is you're going to take, well, actually that works out. You're going to take that distance and you're going to divide it in half. That's the covalent radii. So again, take this distance between the 2 nuclei in a covalent molecule and then cut it in half. That's going to be your covalent radius. And then lastly, they talk about what's called van der Waal radii. And a van der Waal radius is the distance in between molecules. So you take a look at, well, let's say this is molecule number 1. And this over here is molecule number 2. And the distance from a nucleus of one of the atoms in the first molecule, the distance one of the nucleus in the other molecule, that is your van der Waals diameter. The radius is going to be, take that distance and cut it in half. And so the other 3 are intramolecular distances, whereas this last one is an intermolecular distance. All right, so that's chapter 12. And I'm going to stop here before moving into chapter 14, because there's really not a whole lot that I need to go over in chapter 14. I think the video did a really good job with it. So thank you. That concludes chapter 12. We'll pick up chapter 14 in just a few moments. Hey, old person.